Okay. The next theme is a p-adic norm and p-adic distance. Our final goal is to understand p-adic distance. As I said, p-adic distance, in case in our lecture, two-adic distances is the distance between, estimate between two species in a phylogenetic tree. Okay. Then let's see the definition. A p-adic norm. Okay, as we extend ordinal function into a rational number, so based on this extension, we can define a p-adic norm. That's it. P-adic norm is a function from rational number to R that is obviously satisfies norm condition on how we define this. Yeah. If the rational number is non-zero, then we define one of p to the or x at p, and otherwise define as 0. That is clearly satisfies a norm axioms. But when we think about what is a norm, let V be a vector space then we call a normed space. There are three conditions. For any scalar is given, that rule satisfies. And triangle inequality is essential condition. And the necessary and sufficient condition, if the norm is 0, the only way to is 0 vector. That is a norm condition. If we check, when we check these guys is a norm, we will I will mention some points, remarkable points. First, when we verify is a norm, the first condition is changed. P, in that case, that alpha is, because alpha is scalar, that is a absolute value. Okay. But in this case, we should see that we should see that this part. That is a little different from when you compare to the traditional definition of a normed space. That is also, in that case, I will express based on the expression. Okay. Alpha b, when you check this first condition, that also, that is not our absolute value, that is also a normed point. So that is not. That is also a norm. So, okay, that is an absolute value. But in this case, it's not absolute value. This part is also a norm. And second remark is that it is not easy. It is in my opinion, it is a little or somewhat complicated when we try to check triangle inequality without discrete valuation. So if we can verify that the triangle inequality by purely the definition of the ordinal x. But this is for me little complicated. So when we think about discrete valuation, the knowledge of discrete valuation, we can check that the triangle inequality, easily check that the triangle inequality. Because first, I will assume that without general of loss of generality, assume that part. Assume that is here, okay. Then, where that is a ordinal, okay, and the ordinal is defined as rational number, extended function of ordinal p a at x at p, then this means that by the definition, like this, because that function is a discrete valuation, so when you think about the relation, the sum of x plus y by mu is always greater than between two value. In this assumption, that is new x, okay? So, and because when you think about take exponential p, that is also the inequality also valid, but we changed the inverse, take inverse, that should be changed. And p is a prime number, that is a natural number greater than 2, so that is or satisfies this relation. And by assumption, that is vx, okay, so that is also satisfies. So the inequality is changed like this. And if we add sum, that is also positive number, okay, because p is an integer, positive integer greater than 2. That value is whenever the value spew out, that is always positive when you consider exponential function. Then by definition, that part is changed by xp, and that is yp. So triangle inequality, we should check that triangle inequality satisfies. But without the knowledge of the discrete variation, that is really complicated to prove. Anyway, that satisfies a normed axiom, and note that norm space induces a metric by defining by norm if in general case, okay. Of course, in this case is this Q and p-adic norm is given, so the case is that like this, and precisely that is 1 of p or p x minus y. Okay, so this is a metric we call the metric dxy, induced by p-adic norm, a p-adic metric.